Climate change is one of the hottest topic right now and probably will be in the next century. So my name is Normunds Stivrins and let's talk about climate change. Everyone has its own opinions about the climate, and as we see, previous year was in general. The following year is warmer than it was previously, and this we see also this year that 2020 was, let's say, warmer than 2019, and most likely 2021 will be warmer than 2020, and 22 will be warmer than 21, and so forth and so forth. So the climate change is a hot topic. When we talk about the climate change, it's really polarizing views of different from the different scopes, different perspectives, and everyone has its own opinion. But what we see that the consequences probably will be visible soon, and it depends on the time scale what we are looking for the climate change. If to look at the past, we see that over the last 100 years, every year indeed has been higher, showing higher temperatures than previous years, and these temperature anomalies are increasing with every step what we take. And the anomaly, as you already probably know, is deviation from the normal values. So that means temperature anomaly is temperature above the normal or below the normal. There are certain ways how we can extract the information about the climate. One of those is what we use in everyday life, let's say instrumental measurements, sort of thermometer we have everyone in our house probably. Then we use satellites and meteorological station information about the climate. Well, that would give us information about the last, let's say, 100, 200 years in the best. But when we would like to see the general trends on the longer time scale, then we should looking deeper into the past, and then the paleoclimatology comes in this perspective. If to compare, then instrumental measurement, as I mentioned, can cover last 200, maximum 300 years, as it states here. Then with a paleoclimatology, we can cover millions of years. And well, paleoclimatology will most certainly use climate reconstructions and climate models. Well, these both are used by global organizations such as IPCC, UN, European Union, NASA, well, others can also be stated here. And they use to evaluate most effective way of decreasing anthropogenic greenhouse gases and to see how the climate has changed in the past, and what one could let's say predict about the future. There are two types of climate reconstructions. If we go deeper into paleoclimatology, then first is qualitative, which can give us information about whether the climate was colder or warmer, and quantitative, by how much it was colder or warmer. The climate reconstructions provide insights how climate has changed, but they are not saying what was the reason for these changes. And only climate reconstructions give a long-term data on a climate change that can be used to better understand the present-day climate and give some future projections. Yeah, so of course, we can skip the past kind of insight into the past climate and not doing any climate reconstructions and models at all, and just rely on instrumental measurements. But then it probably would not be the most accurate way how to to evaluate possible changes in the climate trajectory for the future. Well, information about the past atmospheric circulation, precipitation, and wind flows can be obtained through the modeling approach. So here is the difference. When we talk about temperatures, we can reconstruct, but when we talk about atmospheric changes and flows, then it's really challenging, and for that we use also modeling approach. So climate models are really complicated, and they work in several multidimensional layers, therefore they are complex, and climate modeling requires supercomputers, which are located, of course, here and there, but most likely located in strictly certain countries where they can maintain all the costs of running the supercomputer. Today, there are several centers of climate research, not only in Europe but also worldwide, and you can imagine that these climate research alliances are tightly linked to support by different kind of data to build up the most reliable models what they can build today. And temperatures are reconstructed from various objects, organic and inorganic. So now we are moving directly into the reconstructions, because that is the main way how we can get evidence-based information about the climate change. The models are relying on algorithms and mathematical equations, while reconstructions rely on evidence. And that's the fundamental kind of feature why we are using both reconstruction and modeling. We can use reconstruction based on, let's say, we find the pollen grain and we reconstruct temperature. Then we can see what would the model show, what kind of results in the past. And when the model repeats the same reconstruction, then we could say, well, this model most likely works well enough, so let's try to model some future changes. And this is how, well, this is one way how the modelers are working, and why we are seeking also for the reconstruction information about the past climate. Every year, thousands and millions of pollen grains are formed, and there is even a palynology science of pollen and other small particles of organic origin. And this scientific field today plays a certain role in not only studying allergies from the pollen, but also from the climate reconstruction perspective. Pollen analysis was one of the first as well in this field, and pollen grains were, and vegetation composition was used to reconstruct climate already 100 years ago. Pollen grains consist from sporopollenin, and which is one of the strongest substances in the nature, and thanks to that, all pollen grains which are falling into the lake or bog, or let's say an ocean as well, they can preserve for hundreds and even thousands of years. And it is important to state that for each plant taxa, there is certain pollen morphological group. So if we can recognize the pollen grain to which plant it belongs, then we can say in what kind of conditions these plants were living today, and then we apply the same rule also for the past, and we say, okay, so if the plant today lives in in that temperature, then in the past, most likely the temperature was similar at that time. Well, it's not only about the climate temperature, but it's also about the landscape change and vegetation succession and species compositional change. And these things matter. And it is good to have more data on this to give more precise reconstructions. Um, in lakes, there are limited oxygen conditions, and under these limited oxygen conditions, pollen and plant microscopic remains, plant remains accumulate and preserve. And this happens every year until lake is actual. Then, when the scientist thinks that he has selected the most suitable site, lake in this case, for his studies, he goes out and takes sediment core from the lake, then brings the sediment sequence to the laboratory, take some kind of smaller samples in certain intervals, analyze fossil pollen, what he can identify from this sequence. Then it's possible to reconstruct past vegetation. The other aspect for the climate reconstruction is to know the present day, the modern day situation, which regions the plants and taxa are living, and what is the modern pollen composition in these areas. And then this pollen information is linked together through the calibration with a modern climate, and then build up a transfer function which says, let's say, if we have pine 20%, then the temperature will be that high. When the birch is lower, then the temperature will be lower. So when we link together this transfer function with a fossil pollen, then we make a reconstruction. So you need to understand that this is based on the vegetation composition percentages, and not only percentages today, but its most common way. We look what was the vegetation composition, and then we can say which plant taxa were dominating, and by knowing in the nature if the plants dominate in certain regions, we see that these regions might have certain temperature. Yeah, it maybe sounds complicated, but I think from the picture you can grasp this idea more clearly, I hope. And just one example about the present day temperature significance and distribution. These species are from the North America: holly, eve, mistletoe. Of course, they can be found also in Europe today. But the idea is that each plant taxa has its own optimal temperatures and precipitation kind of intervals in which they live. For this case, it's important to know what is the mean temperature of coldest month, the mean temperature of warmest month, and annual temperature, annual precipitation amount, precipitations per winter or summer, and if possible also some kind of soil conditions that could be taken into consideration as well. So if we know these kind of characteristics for the summer temperature, winter temperature, then take species 1, species 2, and species 3, put them on each other, and then we can get sort of a sweet spot in the middle where these all three species distribution according their need of temperature during the summer and winter. We can say that in this spot all three are overlapping, and then most likely the temperature will be that high. Yeah, and when we talk about Latvia, about this kind of region, then we should consider that all the lakes and the terrestrial ground itself has been ice-free for the last 15,000 years. So that means we cannot reconstruct climate deeper in the past based on pollen data or plant macrofossils because there is no evidence about the previous times because the ice has been moving away the topmost surface from the previous morphological landscape and the soils. So we lack information about more deeper time than these 15 to 16,000 years from organic point of view, from vegetation point of view. Of course, there have been some points where certain information about the previous interglacials can be found, but in general, we are focusing in this region on the last 15, 16,000 years when we know what we are reconstructing, and that includes also the climate. Well, the climate, summer temperature over the last 14,000 years have been changing quite a lot, as you can imagine. So on the x-axis, we on the right you see past, then on the left is present. Always pay attention to these orientations of axes and directions. Then, if we split closer, then in detail, then the late glacial, meaning the last glacial period uh, or glacial period, ended 11.7 thousand years ago. And the late glacial, by this we understand the Bowling Allerod and Younger Dryas period, when the climate was colder and sort of glacial conditions prevail. Then interglacial, which is called Holocene, and then further subdivision of Holocene goes early, middle, and late Holocene. And this division is kind of must to know, because if you know these rough divisions, then it's easier to characterize in general what happened in these episodes of in the past. So let's put some information about the present day summer temperature in Latvia, and then it's probably easier to understand relevance of the climate change in the past. During the late glacial, the air temperature during the summer was way lower than the present day temperature, while we see there are certain time period from 1200 to 4200 years ago when the summer temperatures were peaked higher above the present day temperature, as well as closer to the present day. There are some shifts. While summer temperature was higher, let's say, than today, 8,200 and 4,200 years ago, by 1 degrees approximately during the summer. Then we see that during the winter temperature, during the winters at the same time frame, winter temperature was way up from the present winter temperature by 2 to 3 degrees higher than present day winter temperature. So we see that these temperatures do differ, and it's important because like in nowadays we see that high Arctic or high latitude sites warm higher during the winter than in summer. What is and what are actually these long-term drivers of Earth climate? And here we can look on two major groups or factorial groups: orbital factors And I call them ocean, continental, and morphological factors, which relate to other factors than orbital factors and relates to the Earth. Orbital factors include cosmic radiation, cosmic dust, solar cyclicity, solar radiation, geometry of Earth and the Sun. While this is important because cyclic orbital changes over the time limits how much Earth receives the radiation from the Sun. And not to mention, well, of course I'm mentioning, but at least 1.3 million Earth could fit into the Sun. So its mass is huge enough, and although we are from the human point of view far away from the Sun, it still influences the climate on the Earth. And how we can recognize this, that the Sun is influencing our Earth, is just to look outside. That when we have strong solar eruption, we see aurora borealis. Um, Solar activity uh, is cyclic with a certain cyclicity, and there is 11-year cycle for the Sun when the spots of the Sun first when the solar cycle begins. The sunspot number is low, but while it's reaching its maximum, the sunspot number um, is the highest, and then again it lowers. The sunspot monitoring began in 17th century already, and today we are still looking how these sunspots appear and where. And when we hear about the uh, geomagnetic storms, these most likely are linked to the sunspot activity. Like well, we can hear now and then that sun has some sunspot has erupted and towards the Earth, and therefore we might expect some geomagnetic kind of storm on Earth. Yeah, so this is related closely to the sunspot activity, and that means also the radiation it erupts to us. And as we have so long record of the sunspot activity, then we can see also certain things and features like Maunder minimum, Dalton minimum, which are indicating the low solar activity as and radiation itself. Then we have, let's say, modern maximum to like in the over the last century, 50 years, I would say, and the number spot, the number of sunspots is rather cyclic, as you can see from the graph. Well, as regard for these minimums, it has been attributed that the Little Ice Age from 12th to 19th century, which was um, taking place in Europe, when we see that for instance, in Netherlands, in Central and Eastern, the Western Europe, ice was forming on the rivers, and colder periods were in Europe, and it therefore it was harsh conditions for certain time periods over this multiple century time period. And one of the reasons what are mentioned there are due to the sunspot activity, in this case low sunspot activity, lower radiation values. According to estimates, we might expect lower solar radiation in the following next century. And every next sun cycle is will emit lower and lower um, this radiation. So that means also less warmer conditions on Earth. Of course, we need to see this somehow, how this might influence us. And there are climate modelers who have picked up this information and tried to test possible outcome due to the decreased solar radiation. And what these models show that the frost days will probably increase by at least 6 days for our region, and on average, air temperature might decrease by 0.5 to 1 degree in our region, and but we need to consider to take into account that these are models where only the impact of solar radiation has been modeled, and not all ingredients have been taken into consideration. Not to mention that solar radiation, when we compare to other influences of different sources, uh, influential on the climate, the solar radiation, the sun's impact on climate is minimal on short time scales. Yeah, as we see that CO2, methane, also nitrogen gases are stronger than the sun's, the solar radiation. Therefore, these gases tend to warm climate. While, interestingly, aerosols can have both warmer and colder effect, and in most cases in the past, these have been exactly getting cooler climate than warming. But the sun's impact on the climate is minimal on short time scales, yeah, so that can be stressed here. But while it's on short time scales not so influential, the long-term cycles drives ice ages and interglacials on Earth. So this is a major difference. We cannot rule out the sun's importance because we are talking about when we talk about Earth history, sun has been kind of the major source for the uh, driving ice ages and interglacials. How do we know about this? Well, we can see in ice cores, let's say from the Greenland and Antarctica, where we can see the small bubbles which were formed, trapped during the ice formation. And when we melt these ice samples with the bubbles inside, which hold information about the past atmospheric composition, we can reconstruct what it looked like, what were the concentrations of the certain elements and gas concentrations in the past. And what we see, there is a clear sign that glacials and interglacials have been repeating all over the place. So that means there have been cold periods and warm periods. Again, cold and warm. And now we are living in the interglacial, meaning that before that we had 90,000 years of glacial conditions, and now we have 10,000 years of interglacial conditions. From the graph, you can see that the tendency is that, well, the average length of the interglacial commonly is 10,000 years. But we already have lived almost 12,000 years in this interglacial. Therefore, uh, the next glacial should come at some point, but as we all are aware, then the human most likely have pushed this next glacial further into the future, if at all it will come. So, but what defines whether it is ice age or interglacial? There are certain factors which we must consider when we talk about the interglacial and glacial formation. Earth orbital eccentricity changes over the 100,000 years. Then we need to consider also Earth tilt. So that means that there is an angle which changes from a certain point to a certain point over a 41,000 year period. Then Earth is not rotating around itself in a, let's say, uh, in an easy manner. It kind of wobbles around herself. And this we call precision, which changes over 19 to 23,000 years. And if these put together, then of course that means that if there is not, let's say, no Earth tilt, then the sun rays would evenly distribute with the highest peak on equator. But um, as we see that we have this tilt against, if we look to the sun, then the sun rays at certain point heats more northern hemisphere and then southern hemisphere. And then, if consider this tilt, this then is important how much sun radiation or heat northern hemisphere gets. So when we have closer to the sun, this northern part, then it's warmer. When it's further, then it's colder. The link between CO2 and temperature. There's a high discussion in not only within the scientific community, but also I would say more discussion outside scientific community, because scientific community has agreed upon that we see that CO2 has a close correlation between climate warming and not only climate warming but also climate cooling when we see changes in CO2 concentration in the atmosphere. But how it all starts, how we get out from the glacial cycle. So when we have all these kind of precision, tilt, and eccentricity, and the kind of a geomorphic orbital location, Earth location against the sun radiation, then we might see that the temperature will slightly increase. And when it happens, then Arctic gets warmer, ice melts, fresh and cold meltwater flow into the ocean, then disruption of ocean occurs, then the hemisphere differences see the differences in warmth conditions. During this time, then we see that the CO2 dilution decreases in the southern hemisphere oceans, and then that means that more CO2 emits to the atmosphere, the concentration of CO2 in the atmosphere increases, then air temperature increases, and we are getting into an interglacial condition. So that means orbital cycles initiate warming, which is then amplified by 90% due to the increase of CO2. So we need this temperature increase, which is small but still enough on the longer time scales. Yeah. So, and we are not talking about 1 year, but over the thousands of years, this warming is getting higher air temperatures, and that then initiate increase in CO2, also other gases, but in this case, let's talk about CO2. Then it initiates CO2, and then it starts overdrive or amplify the climate warming further. And therefore, we see when we have higher CO2, then also the temperatures are getting higher. But the first switch was due to the temperature increase, and then it was overwhelmed by these other processes. Not only gases, but also tectonic processes are of high significance. Lithospheric plate tectonics. This is why, because we see when tectonic plates collide, they form high mountains, and during that long period, mountains erode and weather. And during the weathering, atmospheric CO2 is taking a part in the weathering process, especially with the silicate. And due to the weathering, different kind of products are getting into the ocean and settles into the ocean. Therefore, on a longer time scales, thousands and millions of years, CO2 decreases from the atmosphere. In the atmosphere, it decreases, and therefore climate cools. Yeah, and one such example is collision of Indian plate with Eurasia 50 million years ago. And still, Indian plate moves with a rate of 67 millimeters per year, so this movement has not stopped. Uh, what we see then Himalayan mountain ridge resulted in cooler climate in Eurasia and North America. If before Tibet um, region was moist and something actually grow there, then after the mountain ridge formation, the heat and moist was trapped, and therefore uh, this moisture falls and are left in Indian and Nepal region, while Tibet plateau is dry. And yeah, and thanks to them, other collision like 3 million years ago, North American plate collided with South America, and Gulf Stream formed, thanks to which we can live at such high latitude as today. Otherwise, it would be similar as in Canada. Northern Canada. And more pronounced glacial periods reoccurred in northern hemisphere, specifically due to this reason, and cyclic glacial and interglacial episodes over the last 3 million years have been occurring with a cyclicity. But why? So let's say we have warmer and saltier Gulf Stream now after this collision, and which flows to the north. So we have saltier and warmer shallow current which goes to the northern western part. Then this warm water evaporates, and with wind dominated to the east, east dominated wind direction flows into the Siberia. So water evaporates and gets into the Eurasian continent. There it falls out either as rain or snow. Then rain and snow accumulates. Well, snow can accumulate for years, and in general, water flows through the Siberian river system to the Arctic Ocean, where it freshens the Arctic Ocean, and that amplify or increase the sea ice formation. That again amplifies solar albedo, which increases, and therefore Arctic Ocean gets cooler and fresher. Yeah, so that then influenced the Gulf Stream in general, which have got saltier due to the evaporation. Yeah, so when water evaporates, this Gulf Stream gets even saltier. Then when it's reached northern part closer to the Arctic Ocean, it cools down, and when it gets cooler and it's salt water, then it starts to sink, and then it goes deep into the current. And this we can follow today that this current is still active, and it doesn't start there and doesn't stop there. It is connected through the world, and while we see certain flows are on the surface, like a Gulf Stream, then when it cools down and sinks, it starts its own journey again through the bottom of the oceans, and not only North Atlantic Ocean, but it goes way through the other oceans like Indian Ocean and Pacific Ocean and around Antarctica. And it takes approximately 1,500 or 1,000 years in certain cases when this sinked water again sees the sunlight. So As you can imagine, that's quite a lot of time, and therefore we can say that the ocean currents have, or water has this kind of a memory of events. So that means the water is bringing also some elements within this current. But today, what do we see when we consider climate change and climate warming? We need to think that the ice melts, and that what we see is disrupting the Gulf Stream. As ice melts, it cools it's cool and fresh water, and therefore it mixes with when it mixes with the Gulf Stream, which is salty and warm, it gets cooler, and therefore the Gulf Stream today we see it gets slower thanks to this process when it is disrupted. So, and what consequences it will have? Well, we'll see. But what we see already, there are more and stronger storms in North America. But that means also colder conditions in our region. At the end, of course, we will see what impact it has. Sometimes also volcanic eruptions are blamed for the climate change, and some claim that the volcanic activity is actually stronger than other processes, but well, like humans, yeah. But sure, during the volcanic eruption, a variety of material is emitted, but whether it's stronger enough than the human, well, let's see. Gases and microscopic volcanic particles, which we have a term tephra for that, in the atmosphere and troposphere reflect sunlight and in most cases cools the climate. So while there is eruption, gases and microscopic volcanic particles, if they get into the atmosphere and troposphere, they reflect sunlight and in most cases cool the climate. Yeah. Uh, we have found also in Latvia that there have been some historical eruptions and their clouds and particles from, let's say, in this case, from Icelandic volcano Askja 1875. These small particles have been covering also Latvian ear. And we can say so because we found tephra shards, cryptotephra, in 3 sites. These are Pikata Lake, Karash Lake, and Bog Teichi. And all these particles indicate that we are not so secured from the any volcanic activity because these clouds can distribute long distances and have not only climate cooling effect but also influence the organic organisms like humans and animals. If the, let's say, concentration of these shards is high enough when inhaling and eating, let's say, like animals eating the grass, they can damage their inner parts as well. Yeah, but again, if we see this, let's say, in our region, at least in 1875, then we can say that certain conditions prevailed and this eruption was strong enough, emitting high enough material that reached also our territory. Um, Another example how climate influences the climate, and again its cooling effect. In 1815, there was a huge, enormous volcanic eruption of Tambora volcano in Indonesia, which, as you know, is located in the southern hemisphere more, closer to the equator. Then we see that in 1816, the next year was cold, cooler during the summer in Europe. So, and historians refer this as year without summer. So 1816 was 3 degrees cooler than normally it would be. And therefore, the people witnessed harvest failures, illnesses related to this, and probably it was not so easy to live in these conditions when you're living kind of success is depending on the harvest and the amount of you eat. Next example is about the eruption of Laki volcano. Again, this will be from Iceland, and this eruption lasted from 1783 to 1784. So 1 year around, there was eruption which emitted mostly gases, and these gases were influencing the whole northern hemisphere. Like through the summer and winter temperature decline, and they were below the average temperatures in northern hemisphere by let's say 2 to 3 degrees lower in Europe. And as these kind of conditions also influence climate, then again the crop failure and food prices went up, and illnesses increases in plague exploded again, and social pressure was that high that this in his history is assumed to initiate also the Great French Revolution. So volcanic eruptions and climate change on short terms and longer terms influence human lives, like in this case French Revolution began. Annually, volcanoes emit 280 to 360 million tons of CO2, while human emits yearly 39 billion tons of CO2. Yes, a million to billion comparison. Therefore, if to consider the last century, we have not seen or not witnessed increased volcanic activity. Therefore, this is again kind of a link that we have something to do with the climate change also here, not only to blame other natural cycles and episodes of eruption, let's say. And as you got the impression that the climate eruption most likely will cool the climate, not to get warmer due to other reasons. Well, CO2 concentration in the atmosphere have been different throughout the Earth history, and while at the beginning of Earth life, atmosphere dominated by CO2, which later was consumed by one of the first living organisms on Earth, cyanobacteria, we see that when cyanobacteria consume CO2 from the air and as side element emit oxygen, increase of oxygen cools the climate, which is, I think, makes sense, because when we see more CO2, then the climate gets warmer. When we see less CO2 and more oxygen, climate cools. And this has been led to a substantial decrease in greenhouse gas concentration in the geological past, when the climate actually got so cold and that we witnessed full glaciation of Earth, and this is referred as snowball Earth, and it most likely have not been only one case, but probably even more. Therefore, increase of oxygen, climate gets cooler. So therefore, from CO2 atmosphere to the oxygen-rich atmosphere, and vice versa, all must be in balance to ensure a life on Earth. Greenhouse effect gases in the atmosphere varies, and the major is water vapor, which forms 95% in total from the old atmosphere gas concentrations. Of course, then comes other gases like also CO2. And the water vapor is the most significant greenhouse gas, as you may know, and importantly to underline that the water vapor is nearly 100% of natural origin. Of course, we need to pay attention to anthropogenic greenhouse gases, and this is a carbon dioxide, which forms 84% of these gases, and there are also other gases which are crucial for the climate. Without greenhouse gases, actually, in the atmosphere, the Earth's average temperature would be minus 16 to minus 18 degrees. So we need greenhouse gases, but again, there must be some balance. Not only CO2, but also the methane and nitrogen gases are important. And what we see from the Greenland ice core data for methane concentration reconstructions for the last 12,000 years show there have been some increase from 12,000 to 8,000 years ago in methane concentrations, then lower values, and then over the last 4,000 years there is an increase in methane concentrations. So the question, of course, whether this is related to human activity. If to see the source of the greenhouse gas points, like when was the highest methane increase, we see that it took place around 12 to 10,000 and around 4.2 to 3,000 years ago. And after that, we can conclude that there is some other possible lineages for this methane increase. Scientists have studied not only Greenland, but also bogs and lakes, and let's bring in bogs and peatland. It's possible to establish the date of the bottom layer of the peat by dating it using C14 dating method, and then we can get precise date when the bog was formed. And if we core in several bottom places over the bog, we can say how long time it took to establish for the bog and spread out for the bog. At first, bogs start their life in a certain place, which probably is one point from which it expands to the side. And these dating methods and approach has been applied for the northern hemisphere peatland areas, and what scientists have found that the peatland expanded at from 12 to 10,000 years when the climate was warm and enough and moist. Then the climate was warm and dry within the 8.2 to 4.2 thousand years ago, and then it switched to moist and cooler climatic conditions. And this is when we have more more humidity and moisture, and less. Moisture is more than evaporation rate. Under these conditions, new bogs are forming. In their emission phase, they are forming fen-type bogs, which means there is higher water levels and higher methane emissions. So, and this fits well with the Greenland ice cores. So that shows that the natural processes also can influence the methane concentrations in the atmosphere, while of course they can also limit these emissions. Peatlands store approximately 30% of whole carbon reserves, and peatlands in the northern hemisphere stored 23 plus minus 2 tons, or what was the value in this case? It dropped out from the head, but gigatons, most likely this was carbon per square meter per year. So for almost 12,000 years. And thanks to high amount of carbon capture and storage, air temperature is 1.5 to 2 degrees lower than it would be without peatland. So there is high correlation to that. During their photosynthesis, bog vegetation capture carbon from CO2, and therefore bog is a superb carbon storage. While we have enough high water level, then the bog will store carbon. So that means any water level manipulations influence carbon accumulation rate. Oh, yeah. So if the water level is high enough, we have carbon stored. So that means if we have warm and moist, like we are in these conditions when the climate is getting warmer, then if it's enough warm and moist, then more carbon will accumulate if the water level is high enough. While if the climate switch to warm and dry, then the water level will drop, and we'll see that more carbon will be lost. So more CO2 and methane, more CO2 in this case will emit from the boat. Our studies from Latvia have shown that climate warming increases carbon capture and storage in Latvian bogs due to increment of primary productivity of vegetation. So longer time period for photosynthesis, also growing season as such, and enough moisture level. So under climate, under warmer climatic conditions, more carbon can be stored in Latvian bog. Bog age annually accumulates 169 grams of carbon per square meter. So, and this average value is pretty high. And if to compare the carbon accumulation per vegetation type, then homotrophic bog is capturing higher rate of carbon than boreal forest soil, for instance. Which still, of course, boreal forest soil is good that we have them because they store carbon. But if to compare, then these kind of places and sites as bogs capture more carbon than other sites. And that's thanks to different kind of species and also, again, moisture conditions and these kind of aspects and factors. The topmost layer at bog is rich in oxygen, and therefore CO2 and nitrogen oxides emits. But if bog is moist, then methane will emit, while minimal CO2 and nitrogen emission, or even no emission of those elements. We then need to find sort of a balance where at which depth the bog is the most helpful for the climate and not changing it. So if bog is dry and water level is deeper than 10 centimeters, we see that there is a change in greenhouse gas emission. The lowest most global climate warming potential is at water depth of 10 centimeters from bog surface. So that means at 10 centimeters of from bog surface, if the water is at that depth, we get the lowest emissions from greenhouse gases, and not only from CO2, but combining CO2, methane, nitrogen oxide. So if we can manage to keep at that height, at that level, at that level, the water level for the organic soils, then most likely we can succeed to reduce emissions of greenhouse gases. Um, Taking into account land use change, and forestry, LULUCF, new direction at national and European level, greenhouse gases can be decreased if one can act to implement necessary changes and take into consideration natural possibilities. For instance, on the graph on the bottom, you can see carbon removals. On the top, LULUCF emissions. So what we might expect potential by 2050 in a green and shaded kind of a area, we expect that organic soils will store more uh, carbon. Agroforestry, forestry and agricultural field activities also will switch to removing carbon from the then emitting, and so we are in a way to see some dramatic changes in a way how we are managing our landscape, our fields and forests. So one option for the organic soils, for instance, are paleoculture, which is the productive use of wet peatlands and organic soils, like agriculture and forestry. Yeah, so we can plant these kind of different things there. And for the peatlands and organic soils, well, for the peat, we see that peat under natural conditions in Latvia, in Teichi, for instance, per year, could accumulate 4 millimeters per year. So is it high enough or high enough values? I would say definitely. So, and these kind of aspects should be taken into consideration when we think about kind of climate, where to store the carbon. So we might use peatland and organic soils to store more carbon for the tackling tackling this issue about the climate change. And as we showed today, then we have, as I showed today, then you see we have some possibilities. And by the way, in Latvia, we have almost 11% of whole our territory is covered by peatland. So we can think wisely and act wisely and use these areas to implement, for instance, polyculture or recultivate them or renaturate these sites, grow on wet conditions, let's say forests or uh, certain plants, which can then be used also in economy, while also these areas allowing to accumulate more carbon. Uh, So different kind of interesting features from scientific data we can extract. And uh, again, thank you and see you next time. It was my pleasure to introduce about the climate change.